Hello again. This is Math 2233 coming to you from the College of DuPage, and the title of this lecture is Line Integrals, the Fundamental Theorem of Line Integrals. As always, please be an active learner as you watch this video. Recall back in Calculus 1, in fact, you studied a statement of the fundamental theorem of calculus that was written this way. The definite integral from a to b of f prime, capital F prime of x, dx is equal to f of b minus f of a, where f prime was continuous on ab, and we, in fact, in our textbook call this the net change theorem. In words, the integral of a rate of change is the net change. If we think of the gradient vector, del f, of a function f, and this is lowercase f, of two or three variables as a sort of derivative of lowercase f, then the following theorem could be regarded as a version of the fundamental theorem for line integrals, and that's what, in fact, what we call it. Let's have a statement of it here, and note the parallelism. Let C be a smooth curve given by the vector function r of t, where t runs from a to b, and let f be a differentiable function of two or three variables whose gradient del f is continuous on c. Now you see, so this is what we were talking about as being kind of like the derivative, and this is the dot product, not a product like this of dr, but r runs from a to b along the curve. And so then this is the potential function, and this lowercase f is the potential function associated with del f. So this is true, and so the integral over the curve C of del f dot dr, dot product dr, vector dot product dr, is equal to f evaluated at one endpoint minus lowercase f again evaluated at the other endpoint. This is the final endpoint, this is the initial endpoint, and you can see that this is a very parallel kind of statement, but we have to prove this a bit. Let's talk about what it means, though. This is the theorem. So what it says is that we can evaluate the line integral of a conservative vector field, and that's what it means, that there's a relationship between f and del f. So if we have a conservative vector field, the gradient field of a potential function f, then simply by knowing the value of f at the endpoints of C, we can evaluate the integral. We don't have to worry about parameterizing the curve and all of that if, in fact, f is a potential function. And so that means we can do, in two dimensions, we can evaluate this function at f of x2, y2 minus f of x1, y1, or in three dimensions, as we said, by taking f of x2, y2, z2 minus f of x1, y1, z1. A great simplification in terms of the calculation. So let's look at the proof of this, and we're going to do a proof really by calculation. So, and recall that r of t represented c. So when I have this dot product of these vectors, well, this is what we have, and dr is r prime of t dt, and r prime of t is dx dt, dy dt, dz dt as a three-dimensional vector, and del is the gradient, and so that is going to be partial of f with respect to x, partial of f with respect to y, and partial of f with respect to z. So when I take this dot product, I have this expression dt, and we go from a to b because that was the parameterization. But this by the chain rule is exactly the derivative of f of r of t dt, because the chain rule says you do this down each of the, we called them trees, I think, in our class. So you see, this really is now a function of a single variable. This is the derivative with respect to t of this dt. So it really, now we've changed this through this calculation into a Calc 1 problem. So this is going to be f at r of b minus f at r of a. In addition to helping us calculate this, there are many important applications, including the following, and actually all of these have to do with gravity, and so that makes it a conservative vector field. So a cell phone manufacturer can use the fundamental theorem for line integrals to determine the amount of kinetic energy your cell phone will have if you drop it from a certain height. Again, that's a potential function. The gravitational potential energy becomes the gravitational potential energy becomes kinetic energy, 1/2 mv squared as it strikes. Similarly, a NASA physicist planning to launch a satellite from the surface of the Earth into low Earth orbit can use this to find the work done by gravity on the satellite in order to determine how much fuel will be necessary for the rocket carrying the satellite to complete its mission. Having enough fuel is an important thing, especially if there are people involved in this. It's important anyway, actually. And here, a hydroelectric engineer can use the fundamental theorem for line integrals to find the amount of kinetic energy a waterfall will have at the bottom of the fall in order to determine how much electricity can be produced. Again, all of these really have to do with gravity. Now, although we have proved that theorem for smooth curves, we should note that it is also true for piecewise smooth curves. And we're going to use this when we talk about the general statement of Green's theorem. This can be seen by dividing the curve C into a finite number of smooth subcurves and adding the resulting integrals. So let's look at an example then. So find the work done by this gravitational field. This is capital F of x is equal to minus m, big M, g, over the magnitude of x cubed times x. Now you should really notice here that this is a vector function and x is a vector, so it really represents x, y, and z, pointy bracket x, y, and z. And here what we have is a scalar function m representing mass. This is the big mass, like the Earth or something, and this is the universal gravitational constant. And this is the magnitude of the vector x. And so if this is pointy bracket x, y, and z, then this is going to be the square root of that cubed. Okay, so find the work done by this gravitational field in moving a particle with mass m, so we're just letting that be the mass, from the point 3, 4, 12 to the point 2, 2, 0 along a piecewise smooth curve C. You know what to do. Let's see how you did. Well, we want to recall from earlier discussions that we actually went through an argument like this before. We noted that if f, lowercase f of x, y, z is equal to this function, and this is Newton's law of universal gravitation. So this is going to be m, little m, big M times g, and this is the distance. Then the gradient is going to be the partial of f with respect to x, with respect to y, and with respect to z. So you see what happens is that this function along here, where I've taken those gradients, and you should verify the calculation, but this is going to be the gradient of f. So you see this is a situation where we have a potential function. And notice that the thing that we're integrating in our example is this capital F, which really is equal to this expression down here. So this lowercase f of x, y, z is in fact the potential function of our capital F of x, y, z. Okay, so once we have that, then the calculation is pretty clear. The work done is the integral over c of f dotted with dr, because that was the definition of work along a curve. And that this f is actually the gradient of this f. That means it's a potential function. That means it is conservative. That means that our theorem applies. And so we have f, which is this one evaluated at 220, minus this f evaluated at 3, 4, 12. So I plug in the numbers and I get m, g. So this is just a big old constant, and then I plug in these and I get these numbers. That is an exact answer. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless y'all.